Hello, everybody, and thank you so much for joining today's Charged EV Engineering webinar. The topic of this session is sustaining high temperature DC link film for 800 volt plus SiC inverters, and it's brought to you by Peak Nano. Now, there will be a Q&A session after the discussion, so please do submit your questions, but at any time during the presentation by clicking the Q&A button that you'll find on your screen, and a recorded video of the session will also be available to view on demand after the event is complete. And you just need to go to this page, this webinars registration page, and you will find the link to rewatch or share with colleagues. But let's get on with today's presentation. So I'm going to introduce our speakers today. We have Pam Wilson, Director of Field Engineering, and Sean Walsh, CMO, both from Peak Nano. Welcome, and over to you.
Thank you very much, and thanks everyone for joining us today. I appreciate you taking an hour out of your schedules to spend some time with us. So one of the things we wanted to chat about today is what's happening in the DC link world, in particular around 800 volt and silicon carbide inverters. While they've traditionally been thought of as just a EV and power charging thing, we're also starting to see them come into DC data centers. So I think the market for this type of technology is going to see an expansion in growth and importance as people look at these technologies over the next 5 to 10 years. Now, today will be predominantly focused on the EV sector, but I think it's worth noting that the data center market is also going to be leveraging the same conversation that we're having right now. So when we think about what's happening, I highly leverage data from our friends at Bloomberg in terms of looking at the overall market. But if you look at the growth of EVs globally, and in particular with BYD out of China, getting upwards of 35 million vehicles, there's an average of 1.3 motors. So some have one motor, some have two, some have four, depending upon what you're doing. At 1.3 motors, that means we're going to be selling a lot more DC inverters. But the other big change in this will also be the transition from 400 to 800. And the thing that really is growing dramatically are the public charging stations. So going from around 4.5 million to 47 million. So that's going to be a huge jump, and that will continue to accelerate as people put more of these in their homes as well. And as a percentage of new car sales, globally, EVs are set to overcome petrol engines by 2035. And if you look at other markets like the Scandinavian countries, China in particular, Japan, Korea, those numbers are already well above 50%. It's the US, Canada, and other markets that haven't quite caught up. But all of this means that, A, we're going to be selling a lot more kit in the world, but it also means that we're also going to see incremental technology changes. And as we know in the automotive world, because of regulatory reasons, because of safety reasons, when you make these changes, they have to be bulletproof. And that's a large part of what we want to talk about today in terms of how do we get to that highly bulletproof standard. So this is a further breakdown of the EV vehicle adoption, but looking at what percentage will be 800 volt over time versus the 400 volt systems that we see today. And probably not a big surprise, you're going to see it in the bigger vehicles first. So all those Amazon and FedEx and UPS EV vans that are out there, you'll see it in buses, you'll see it in some of the other two and three wheeler type vehicles. And yes, it's going to make a big difference on the passenger side, but that will lag behind the rest of the market just a hair. But the volumes of this should cross over again about 2035, where over half the cars will be shipped with 800 volt. And the same thing on the charging side. So still going to see a lot of 400 volt out there because of the price point, but we'll see more of the fast 800 volt charging in the commercial sector. So you'll see them at hotels, you're going to see them at shopping malls. You're going to see them more in public places, certainly petrol stations, which I guess we're going to have to rethink what we call those things now because they're not petrol stations anymore. Um, but the other part is that, one of the hindrances to EVs has always been charging time, and this really, really addresses that charging time as we go forward. So why are we making this transition? A couple of big things that lead into this. So when you look at the trends, it's the technology. BYD and a number of the other Chinese companies, Geely and others, have really mastered this technology. They've made it cost effective, and they've been able to produce it in volume. So that is a significant part of where that push is coming from. This also drives into the charging side of the world as well, where they're also leading in that technology. But there's implications through the entire ecosystem when you make these types of technology changes. And that's a large part of what we want to cover today is what's changing in that ecosystem. The other part is batteries are getting bigger, they're able to hold more, but the demand for performance, the demand for distance, the demand for longer usability continues. People ultimately, at the end of the day, would prefer to never ever have to charge their vehicles. If you look at what's happening again in some of the Scandinavian countries, where they can literally charge as they drive along the road with circuitry that is embedded inside the infrastructure, that is also another reason why this transition is happening. So again, when we look at the new EV sales, how is that going to grow? Upwards of 40% by 2030. So that is a really, really fast transition when you think about it. So there are mainstreaming of major platforms. So from IKEA, from Kia, Volvo, BMW, next gen Toyota. Um, at the high end, you've got Lucid, Taycan, Rivian, and a number of the supercar vendors are also using these. But at the end of the day, the biggest player in this is BYD, and they will drive the standards, they will drive the adoption rate, and they are going to drive the global market in this direction. So, in terms of how we see this happening, again, we're kind of have a growing adoption rate over the next 3 years. Then you're going to start to see it push more into the mid-tier of cars, and then it will roll down into the budget and the compacts. And by 2033, 2034, this will be the default. And I'm sure there will be another transition over the decade that follows that. But make no mistake, this is coming and we have to prepare for it. So why is this happening? Well, there's two other dimensions in the architecture that are enabling it. Number one is the efficiency improvements that you're getting from silicon carbide and gallium nitride. And then the move to megawatt-based charging systems. Because we want speed, and speed comes with higher frequencies, and higher frequencies come with higher heat. And this is the implications of moving to that 800 volt. So you get better efficiencies, you get faster charging, you get a number of other things, but it creates challenges in the design environment, predominantly in the form of heat and the need for new components. So this is where we want to be able to make some pretty significant changes, not only in the control circuitry, but in everything else that goes around it. Pam had made a comment that resonated with me at the PCIM show, which was if we can shrink capacitors by 20 to 25% and still support this, what can you do with that extra savings? You get greater distance, you can put more capacitance in them and have finer granularity of control over power distribution. You can shrink or increase the size of the motors as you need to. You can remove cooling infrastructure that you currently have to have with the current generation of capacitors that max out around 105 degrees. So all of these different design decisions also roll into the bill of materials. and ultimately drive towards the fundamental goal of reducing weight, increasing battery life, increasing battery efficiency to get greater distance. At the end of the day, that is what drives everything related to this EV world. Sorry about that. So what happens? Sorry, guys, got hit the wrong direction on the buttons. So when we think about what this means in terms of units, um, getting to 14 million cars means we're going to have probably something on the order of 20 million different inverters going in. That'll be 800 volt, and this market is still continuing to grow. So when we think about why this transition is happening, not a big surprise. Lower the current, less copper, lighter harnesses, less heat resistance, less cooling, more headroom for fast charging. And it all boils down to improving the fundamental performance of cars. But that performance increase comes with an operational challenge, which is heat. And we're going to talk about how we address that as we go forward. So, where are the gains coming from? The move to silicon carbide, so faster edges. And again, this really has to do with how does that signal get in? How efficient is that signal going to the motors? Does the motor know how to react and when? The ability to, again, support smaller magnetics, smaller systems, yet yield higher power density and less cooling. And again, this lowers bill of materials and takes other infrastructure out of the system that you no longer need. So when we look at this conversion rate down, somewhere around 52% will be moving to the silicon carbide as we go forward. And of course, this is going to mirror the transition of the 800 volt market move. So we think about where this changes in terms of range and batteries. So one of the biggest concerns with batteries today is A, is there a fire risk? And then B, the cost of replacement. I don't think that most consumers still understand what a large percentage of the vehicle infrastructure the battery is. And there have been a lot of stories where consumers are absolutely shocked about this. So instead of having a $10,000 or $15,000 bill to replace your battery system, we can keep them healthier. We can make them more efficient by reducing the heat, and that allows them to last longer and not have the same level of degradation. It also means that you're getting longer range because you've got more efficient use of the existing batteries. One of the other opportunities here is to actually shrink the size of the battery, which can also lower the cost of the car again. So you have that trade-off between increasing range capabilities, even with bigger batteries, with the space that we can save on the capacitor DC inverter side, which will give you longer range, or you can hold the battery constant and have extended range, or you could choose to actually shrink the battery and maybe have a little bit less range, but your price point changes dramatically. And again, because we solve the thermal issues, it reduces cooling systems and other overhead in the bill of materials. The big net change, time to charge. People do not want to sit around and wait for this. We have a mental paradigm in our society of I pull up to a gas station, I fill up, I'm gone in a few minutes. And every single minute that we can reduce this is going to drive adoption. And that will just continue to accelerate this market as we go forward. I fully expect that we will see this 18-minute charging time probably come down into the sub 5-minute range as we go forward for the vast majority of cars. I know there's extremes where they can already do that, but for the average consumer car, I think we'll see 40 go to 18 and go to 5 over the next 10 years. So when we talk about what's changing here in the system, so you've got your controller that's got to change. You've got your DC link caps that have to change because of the temperature that the silicon carbide controller runs at. And you want to be able to get greater efficiency out of the systems. So depending upon who you're talking to, you're going to see total efficiency rise from around 80% to about 95%. So that extra 15% is going to translate into distance. It's going to translate into longer battery life. Um, and it's going to give you the upside for doing megawatt charging, which in turn will also make the time to charge drop dramatically. So this ability to do this core conversion at much higher efficiencies means the charging of the vehicle is going to cost less. You're going to get less time waiting for it, and you're going to get greater efficiency in terms of the usage of that charge. So all of this will translate into the fundamental things that people are looking for in terms of performance improvements. So higher standoff voltage, getting rid of those risks, the ability to deal with faster switching, the ability to put more cells in the same series without fire risk. And, we all know that that's something that, gets a lot of attention. It gets blown out of proportion relative to the total number of vehicles that are on the road. So anything that we can do to mitigate that will also increase consumer adoption as well. Gives you better shutdown safety options, and it also helps you deal with the increased heat that comes from fast charging. So that's the double-edged sword in all of this process, that the 800-volt system creates more heat, but the new technology that we've introduced and advanced conversion has introduced address that need without having to actually add more cooling systems to it, which is the ultimate goal of reducing cost as we go forward. So let's talk about the transition as we go through here. So for the EV makers, they obviously want to push active devices, as do the charging vendors. Power providers, not so much. Improved dielectric, this is where we talk about the capacitors inside the inverters that give you the temperature tolerances along with the rest of that ecosystem. So we're seeing that deployed both in EVs and in the charging side. Uh, the integration re-engineering is much higher on the EV side because generally speaking, the chargers are being dropped in at brand new levels as opposed to retrofitting existing vehicles. Um, and then the overall power system demand is obviously much higher for the power providers at this point because to service the same number of cars, they're having to deliver more voltage to them. So these are some of the overall ecosystem map challenges that are driving the adoption of this next gen. So when we talk about how do we close these big gaps? So for the active devices, it's going to be how do we get passive temperature ceilings improved? For the dielectric, it's going to be looking at new materials where they do not have D rating, so you don't have to put multiple capacitors in, or you don't have to have oversized capacitors that increase the overall size of the DC inverter. So the traditional polypropylene is being replaced by things like nano-layered LDF material, and this will help you deal with the heat issues. Um, You're also changing the engineering, cabling, bus bar designs, all the other things that these capacitors connect to and are controlled by silicon carbide. And each one of these is a small incremental reduction in the bill of material cost and in the complexity and in the number of devices that you need. The other big change here is changing the geometry of it. Instead of having the traditional cylinder Coca-Cola can size capacitors or form factors, we're looking at new technology that have more of a ring deployment, like a giant donut. But what that allows you to do is reduce the impedance and inductance through the system, have better cooling and heat dissipation through the system, and also shrink the form factor to match the deployment of motors and engines and motors and the DC motors inside the systems. And then when you look at at solving some of the system level challenges, okay, pairing chargers, battery storage, that's kind of motherhood and apple pie. You got to do those too. But this change also gives you better thermal design opportunities. It gives you the ability to manage the edge of grid challenges. So what do we mean by that? Um, Getting the conversion from the AC grid to DC down at a higher efficiency, doing it at a lower temperature going into the system, but having the higher frequency rate required in order to do the fast charging. So those are things that next gen inverters help deal with. So we talk about the heat and traction inverter type systems. What are we talking about? So today, the most common material used in capacitors is affectionately known as BOP, which stands for biaxially oriented polypropylene, which is basically a very, very fancy version of saran wrap. Um, but where it starts to have problems is when you get above 85 degrees C. So when we go from the traditional silicon controllers to silicon carbide controllers, the temperature in the environment goes up to around 125 degrees. And you can start to see where once you get above 85, you have significant drops in the capacitance capabilities of BOP-based capacitors. This is what drives the need for adding cooling. This is what drives the incremental cost. And with the next generation material that we have from Peak Nano, we're able to eliminate that. So you don't have to do that. Now you're using smaller capacitors, you got less weight, you've got better inductance in the systems, you've got better geometry for matching the motor housing and deployment, and you take up less physical space in here. And now the question is, what do you do with that extra opportunity? Do you add more battery? Do you extend range? Do you save money and create a new price point for the product in the market? All of these are now options that the the OEM customers have in looking at these approaches. And with the overall cost increases on copper and other base materials in these systems, every time we can add that option to save cost to increase their competitiveness in the market, that's going to be a win for everyone involved in this supply chain.
And I think just to echo on that, a lot of the feedback we're getting is these systems really are being looked at as a whole. What is the total cost of creating that system? So as advancements are happening in the different component sections, nobody wants the capacitor to be the limiting factor here. So it needs to advance at the same rate as the other components.
Not only that, Pam, the other comment that I think you had mentioned in some of your previous communications were that as people are looking at these the not only the form factor of them, but the other infrastructure behind it. Um, there's just so much of that changes. So this, to Pam's point, is going to be an end-to-end process. It has to be new base materials. So we're able to create the new base materials that reduce not only the size, footprint, and cost, but give you higher performance. In the chip world, this would be the classic moment that you would quote Moore's Law, where performance increases but costs decrease every 24 months. And that's a large part of what we want to talk about here. Um, there is ultra high voltage versions of silicon wafers coming down the pipeline that will drive beyond 800 volt that we know are going to drive the next transition in the market. And you have to be ready to support that. And that'll be another part of this equation as we go forward. In terms of capacitors and modules, one of the things we want to do is make sure that we get size down, price down, all those other fun things. And you want to give the OEMs options. The more that we can give the OEMs and the car manufacturers true options for changing their systems, that's where the innovation comes in. One of the things that struck me as we were looking at this is some of the new Ford designs for the factory they're building in Kentucky, where they basically build the car in three pieces instead of a single chassis. So they can change the front end, they can change the middle battery configuration, they can change the back end, and it allows them to mix and match motor sizes, traction systems, distances, and with that common platform across those three-tiered modules, that fundamentally changes the way that they're looking at how they deploy vehicles. And I think the best example of that is they've talked about delivering a $30,000 pickup truck based on that three module system, where the original Lightning EV trucks, while they were amazing, but they were 100 grand. So that's when we talk about the ability to really fundamentally change architectures. That's one of the things we're going for in this. So I apologize. This is sort of the blatant commercial part of our webcast, but you have to endure a few of those things. So this lovely system that we have here for doing the DC converter system, electronic components are always so exciting when you show pictures of them. But embedded here, you've got two capacitors based on our Peak Nano LDF, or low dissipation factor film. The biggest thing here is high temperature support up to 135 degrees with less than 1% loss in capacitance performance. What does that mean? It means this is smaller, it's lighter. They can deploy it in multiple configurations. They can create custom versions of this for every version of silicon carbide controller. So whether you're using Hitachi, onsemi, NGX, take your pick. They have solutions that are optimized for this that can go into your systems and deliver those capabilities right away. So you don't have to wait for this to happen. You've got it all in one kit that has the controller, the bus bar, the capacitors, and they're ready to deploy for development and for testing. And when you talk about where these barriers lie, the most of these systems that are in the 400-volt world come from the biaxially oriented polypropylene solution, which again, once you get above 85 degrees, starts to derate, and now your cost goes up. There's another material called PET that'll run to 125, but it costs 5 times as much and no one can afford it. And then the Pen HV, unfortunately, while it had great capabilities and was sort of in between on the cost, has been end of life. So we think with what we've put together here, we have that next generation solution. We've done this in partnership with Advanced Conversion, who have done all the other design above this. But what they saw in this was an opportunity to restructure what they deliver, to do it with less material, to do it at higher temperatures, to provide better cost footprints, and to create different form factors that better match the deployment of the electric motors that they're supporting. So all of these things were possible because the base materials changed. And we'll see this theme as a recurring engineering improvement opportunity across the EV vehicle and charging sector for this decade, and certainly for the next generation with the ultra high voltage. So when you look at this, again, these have been validated to industry standards, incredibly low dissipation factors, even up to 150 degrees. The ring architecture here gives you the ability to have a much higher communication loop, much better inductance performance, stronger thermal coupling, and the ability to get rid of incremental cooling and other infrastructure that are in the system. And all of this is US designed and manufacturing systems. So what do we see going forward? The megawatt and 800-volt world starts now. We're going to see increased use of silicon carbide, sub 30K cars at that 800-volt level in 2028 and beyond. And then we'll see higher bidirectional power passive electronics. And this roadmap continues for the next decade as we then move into ultra high voltage. But what we want you to take away from this is that Advanced Conversion are building those systems now. It's based on next generation materials that are nano layered. And what that means is that we can improve the performance of those without having to generate traditional new chemistry and new polymers. So just as the chip world can evolve every 18 to 24 months, we'll be able to do the same thing on the capacitance side and be able to march in lockstep with innovation. It probably shortened the silicon carbide adoption and 800-volt adoption world by 5 years because of the heat challenges and the cost challenges that went with it. We now have new technology that will solve that problem for decades to come going forward. So with that, let me open it up to Q&A.
Sean, Pam, thank you so much for a fantastic presentation. Now, yes, we do have some time now for some questions, comments. So if you haven't sent anything in yet for the team, please do so now. You'll see a Q&A button on your screen. But I'm going to hand back to Sean and Pam now. If you can open up the Q&A button on your screens, that would be great. And then start reading some of them out, please.
All right. Where is today's capacitor forcing you to oversize, add cooling, or derate? And how much silicon carbide efficiency does that cost you? So we're actually building a model on this. So to put this in perspective, um, the cooling systems will typically require that you have literally plumbing for the liquid cooling. You've got to have reservoirs for it. You've got to have the ability to have pumps to move everything around. So that's part of the overhead. Capacitors, generally speaking, once you get to that 105 level, even with cooling, have to require 50% more capacitor film. So that makes the capacitor more expensive. It means that you need a bigger box for the DC inverter, um, and that you're getting less efficiency and lifetime out of those systems because of the derating input. So those are all the places that you eliminate excess when you move to the silicon carbide and the efficiency. And in turn, or you move to the silicon carbide environment. To answer the efficiency question, you move from around an 80% level efficiency up to 95% by having the better, higher frequency switching and the precision of those switches, the signal integrity that you get from silicon carbide are a large part of what drive that top level efficiency. This also translates back into battery efficiency. Um, so it improves the entire ecosystem from the performance of the motor through the usage of the battery system.
Sean, there's another question on here, I think that goes with that. Someone is asking if this will help to lower internal battery temperatures as well.
Yeah, it absolutely will because the battery does not have to push power out as much or as often. And it's basically having a receiver of the charge coming off the battery that can accept it more efficiently. So you're going to get less actual usage of the battery storage. You'll have fewer charging cycles, and we're able to pull that out with a much finer granularity because of the silicon carbide signal integrity. That means shorter interfaces with the battery drawing on it. So that's going to reduce heat in the battery. That's going to reduce the risk of cascading failures in the batteries that could lead to fires.
Great. I think one aspect that we didn't really touch on yet has been, if I can find that question again, ripple current, ripple requirements or limits of the capacitor product. Is that something you can talk about?
Yeah, absolutely. That's one of the things I will say that while we didn't specifically design for ripple current in what we did, as it turns out, the nano layering capability really does help here. And one of the reasons for that is it's not a homogeneous environment where if there is an arc in there, it will ripple through everything. With what we do, the layers give us a natural shock absorber, and that allows us to deal with ripple current coming back into the system. It If there is a problem, it stops in one very, very small location. And that's one of the big differences architecturally between the nanolayered system and the monolithic BOP-based capacitors. And the other thing about it is our material is still 90% based on polypropylene, but it's the structure, it's the architecture of how it's put together in the nanolayers and then the glassy material that we put in for thermal improvement. So those two architectural changes are what allow us to manage the ripple current at a safe and much more efficient level.
Great. Maybe this is one that we touched on a little bit in the presentation, but you can elaborate on more. Why hasn't there been advancements in the capacitor area, or what has happened, and where have the limitations been?
Well, I think there's two answers to the capacitor part. One was just demand. When all was said and done, the world hadn't migrated, so that was one of the reasons why they hadn't made the transition. New products are a result of customer demand. And I think a large part of it also had to do that China accelerated much, much more quickly in this market than a number of the domestic manufacturers or European manufacturers. Second is if you look at any new polymer material that goes into a capacitor that would enable them to change capacitors, there's very, very few of them. There's three, maybe four. One of the more prevalent ones, which was Pen HV, was end of life this year by its manufacturer. Um, the polypropylene has been the standard for 40 years, and no one had a reason to change that. And part of it was they didn't have anyone else to go to. So, that was a very, very tough part. So it wasn't necessarily that the capacitor manufacturers didn't want to innovate. They just didn't have the base material in order to do it.
Mm-hmm. Yep. We're getting a few different questions around comparison of this material versus polypropylene.
Yep.
A few around just in general amps per microfarad
Yep.
at the same voltage.
I must confess, I do not know that amps number off the top of my head. There was another question here about how does your tech compare to polypropylene in terms of
Mhm.
volume voltage at per micron. So typically, we can hold 200 volts per micron out to 135 degrees C with, substantially less than 1% dissipation.
There are a few more in here that are more capacitor design specific. I will say
Sure.
for some of those that are very specific, we're probably more happy to answer that one-on-one with your specific requirements for the people asking those questions. So if you have put in the chat something very specific to your capacitor design or end use design, please feel free to reach out to us directly.
Yeah.
Our contact info will be available after the presentation.
Yeah, the one about laser welding, I don't know off the top of my head. Um, I will have to go dig a bit deeper on that. Okay. Could you expand on the overall system level benefits, particularly given a 100-volt bus, using 1200-volt silicon acid, high frequency switching? Sorry, guys, I'm just reading one of these questions here. Could you expand on the overall system level benefits, particularly that given 800-volt bus using 1200-volt silicon carbide and associated high frequency switching allows significant reductions in associated component size, weight, as well as reducing cooling costs? Also, the bus structure needs to be optimized to a much higher degree to realize these benefits. Long question. So again, short answer, where do the system level benefits come in? So one is getting rid of heat. Second is the crispness of the signal from end to end through the system that enables the high frequency switching so that the trigger points inside actually recognize that we have a switching demand request and create the performance. And Everything has to change in this process. You've got to go up and down the entire ecosystem. Um, it doesn't matter which system you're using. If you increase the performance of one component, you have to make sure that all of the others go in there. So it does have to work in harmony from beginning to end. Um, let's see here. Can you share a comparison between electrolytic medical metallized polypropylene and this material given the voltage, current, and capacitance ratings? Um, so we do have a detailed write-up on that. So I'm going to go ahead and send that across. You mentioned PET cost was 5 times polypropylene. Can you give an estimate of what your tech cost compared to polypropylene? It's about 2x polypropylene, generally speaking, depending upon thicknesses and volumes and all the other good stuff. Um, Someone also put a question in here about the EPN material from Bolloré, not Bolloré, from Borealis. We've seen that EPN material in the market again closer to 4x polypropylene, and that's one of the reasons it wasn't adopted. Um, the the market tolerance for 4 or 5x growth in price point just isn't there because of the gross margins involved in the business. So what we've done is we've said, all right, we're gonna probably be a bit more expensive than polypropylene because we're not 100% polypropylene, uh, but we're going to give you back savings because you save 50% of the extra material that you don't have to use with polypropylene. We make the capacitor smaller, we reduce the copper usage in the system, and a lot of the other components around it. So we believe that the net system capacitance cost is less using our LDF material than using polypropylene. Because we consistently get this question from folks going, okay, if polypropylene is X and you're X plus, you cost more. And that is within that one data point of valid observation. But when you look at what does it take to deliver that capacitance to the system, because of all the other things we eliminate, the net capacitance delivery is probably going to be 20 or 30% cheaper, depending upon the configuration of the system.
There's a few questions in here about availability of capacitors using our films. I can answer that one. Advanced Conversion did launch this DC Link this week, so we can send information out there. Yes, our films are being used in those capacitors today, and they are available in a standard form factor, but I believe they also do customization based on your requirements as well.
Yeah, and there are a number of other manufacturers that are looking at that. They haven't announced the products yet, so I can't disclose those. But we can certainly keep you guys informed on that as we go forward. One of the questions here, will you run a comparison versus EPN? Yes, we do have that work being done. It's one of our business objectives for this quarter, and we can share that comparison with this group once we have that research done. I expect it's probably 8 weeks out, to be candid with you, but happy to share that information when it's available. And then someone said, do you have a cross section of the ring capacitor? Um, Pam, did we get a picture of that from PCIM?
We do not.
Okay.
Of course, our partners at Advanced Conversion very much have that and love to show that to customers to show how the system is built, but that's something that we could provide.
Yeah, we can definitely get that. Okay. Do you have some standard form factors that you can show for the advanced capacitors, or is package customization option? So almost everyone, so we're not making the caps ourselves. We're working with partners like Advanced Conversion and Yuchang out of Taiwan and others that pick those. Generally speaking, it's been my observation that the development kits are a standard form factor, but the caps that go into the vehicles are usually custom form factors. But we can connect you with the folks at Advanced Conversion to get more details on that. Is this technology currently? Yeah. All right. So we answered that one. We'll send you more specs on the PP comparison, and we do also have those on our website as well. Just trying to see if there's any other questions I haven't here. Are there any manufacturers who produce capacitors? Yep, we touched on that. We'll send the cross section. We've got that. Can you share comparison with that one we'll have to send that. Even the 15% capacity gain with new materials, the overall charging power creates much more heat per joule. Uh, that's a fact. I mean, that's part of why we developed this film is because it does in fact generate more heat. But we give you something that can handle it without having to put the incremental cooling system in there. Can your capacitor compete with supercaps? Supercaps are a different class. They're solving a different problem than we do. Um, so we do not attempt to do that. We tend to work in partnership with supercaps and designs.
Okay, I
And
think we've got time for just one more question, Sean, Pam, if you want to start working through a final one to wrap up this.
honestly, guys, I think we've touched on everything here.
Great. Okay.
The comment I will make is everything that's in here, we'll put into a Q&A and give you answers to, and then provide links to all the various things we promise we're going to provide links to, and we'll send that out as part of the email follow-up with the presentation.
Absolutely fantastic. And I was going to say to our delegates that you will get a copy. The team at Peak Nano, Pam and Sean, the wider team will get a copy of all of the questions that have been sent in. So if they haven't been able to answer, at the detail that they'd like to during the webinar today, or haven't got round to your questions, you guys are going to, Sean, Pam, you're going to see all of the questions sent in as well. If you've left your contact details with your questions, then they will be able to get back to you directly. I have shared a link to a PDF of the deck that Sean has presented today, and we will be sending out a follow-up email in the next couple of days, which will provide you with a link to the on-demand video of this session and, yes, the PDF of the deck as well, and a point of contact for you to reach out direct to Peak Nano as well if you are interested in learning further information. So otherwise, a big thank you to Sean and Pam today for all your efforts running through so many questions and a fantastically detailed presentation as well. It's been absolutely wonderful to host you.
Thank you. And we
Thank
appreciate
you.
everyone's time today.
Thanks so much. Look forward to seeing everybody soon. Take care.
Bye-bye.